Good. So today we are going to talk about null trajectories. And for this we need to introduce some material regarding null vectors, the concept of null vectors. We've already stated what they are, but we'll do a little more geometry now, a little more abstract geometry now, and then we'll get to null trajectories. What are these trajectories? These are the trajectories of light. So there's an obvious motivation. Until we do this, there's no hope of studying light propagation in general relativity. But light propagation is one of the things that is most important, because that's how we see stars. And those are, these are the huge bodies, astronomical bodies, which experience gravity to a level where, in fact, it's the main thing they experience. So any effect of general relativity will surely be important there. So we have to study this, and it may seem that we have all the material to study it because we went through a discussion of Riemannian geometry and Lorentzian geometry. But there's something missing, which is that this concept has no counterpart in Riemannian geometry. So if you think, from Riemannian we borrowed a lot of things like metric, connection, curvature, Riemann tensor, blah, blah, blah. But we cannot borrow the concept of null vector, because in Riemannian geometry or spatial geometry, it's a theorem, in fact it's an axiom, that if v dot v is 0, then the vector v is 0. The only vector such that its square is 0, that is its dot product with itself is 0, is the 0 vector. And that's because this quantity is a sum of squares. So if a sum of squares is 0, then every term has to be 0, so the whole vector is 0. But in Lorentzian geometry, we can have vectors such that n mu is equal to 0, but n mu is not identically 0. Very much possible. Now here, what does this mean? This is of course g mu nu of x, n mu. So this will, being 0 or not, will obviously depend on what the metric is. But we can look at a simple case. So we'll just look at 4D Minkowski. I wrote this just to emphasize that what I'm saying is not only true of 4D Minkowski, it's true of general Lorentzian manifolds. But we'll illustrate it in 4D Minkowski because it's a very easy example to look at. And you could have worked all these things out yourself. There's no fancy maths in that. Yes?
It should not depend on the
This being 0 depends on the metric. If this metric is different, the same component vector may not be 0, right?
Achha, the components.
Yeah, the fact that this is 0 depends on which manifold we are in. I mean, this is a loose statement. It doesn't depend on the coordinate system in a given manifold, I agree. But supposing I change from one manifold to another in the same coordinates, if something was null in one coordinate system, it may not be null in the other. And in fact, this is since this can be a complicated function, what is null may depend also on where I am in the manifold. This might not be null somewhere in the manifold, and then somewhere else G is varying across all of space-time. There may be some place where the given vector becomes null. Supposing I specify a vector everywhere in space, a vector field, it might be null somewhere and not somewhere else. It's very much metric dependent in that sense. But thanks for asking me to clarify. Now in 4D Minkowski, the classic example of a null vector is that. Okay? And it exactly describes a photon or a light beam which is propagating along the z-axis, and this is its for momentum. Okay, and we'll see that later when we define for momentum in the null case properly. So it's clear that this is null, I suppose. Okay, because this is n. If this is n mu, then n lower mu becomes minus because of the Minkowski metric, And now when I contract these, I get n dot n equals 0. Okay. Now there are many things that one can say about null vectors which are unusual. Let's start with the first observation. We cannot normalize a null vector. There is nothing like a unit null vector. For any normal vector, usual vector in spatial geometry, or even a time-like vector or space-like vector in Lorentzian geometry, I can just divide by v squared, square root of v squared. Any vector v I can divide by square root of v squared. So, and I'll get a normalized vector. So, example, if v mu is minus a, then v mu upon square root minus g mu mu, which is the same as square root of a. If I call this v prime mu, then v prime mu will be minus 1. So for a time-like vector, we can always rescale it so that its dot product with itself is minus 1. It has to remain time-like, but I can pick a convenient number which is 1, so minus 1. For space-like, I can do the same thing, but this will be plus, this will also be plus, and this will be a unit vector in the usual way. But for a null vector, I have n mu is 0. There is nothing like n mu upon square root of this, because this is 0, so this quantity doesn't even exist. There is no such quantity. People are looking dazed, and it is a very dazzling fact. I could have told it to you very early in the course, even during special relativity, but this is the fact. We have to live with it. Can't normalize a null vector. Related to that, there are a bunch of other things we can't do. Okay. So the second thing is, for the second thing, let's talk about hypersurfaces. We actually haven't spoken about them before, but it's a very simple concept. Submanifold of dimension 1 less compared to the manifold. So for example, in 3-dimensional space, a plane is a hypersurface. Okay, so in 3D spatial example, any plane, the xy plane is a hypersurface. It's a submanifold of 3D space, and it's 2-dimensional, right? The yz plane is also a hypersurface, but you can have a hypersurface which looks very strange. It can just be just take a wavy plastic sheet and hold it up. That's a hypersurface, right? You understand what I'm saying? So anything which is 2-dimensional in 3-dimensional space will be a hypersurface. That's the general definition. Now, how do we characterize a hypersurface? You know actually that the xy plane can also be thought of as the plane orthogonal to the z-axis, and likewise for all the other planes. That's why a rotation of x and y is called a rotation about the z-axis, because z is normal to the xy plane. If I had this weird plastic sheet, then of course there would still be a normal vector, difficult for me to draw, which everywhere sort of sticks out of it. And if I knew that normal vector, I could say that this plastic sheet is the surface orthogonal to its normal vector. So from the normal vector, I can find the surface. From the surface, I can find its normal vector. It's again something we are used to. So far, so good.
We can only find the parallel surfaces where.
What do you mean by that?
So xy plane and xy plane shifted by some constant z will have the same normal vector.
That is true. Yes. So you can, that's correct. So okay. So here I guess the problem is that when I say z vector, I didn't say where it's based. If it's based here, then it's the xy plane. If it's based there, then it's that plane. So I assume that I'm talking of a vector which is based at a point. Now in the case of 3D space, I can avoid basing the vector because the z vector looks the same everywhere. So I can just say z axis. That doesn't work. There's no straight axis, coordinate axis in more general manifolds. But if I have a vector, just a vector, remember, is an infinitesimal thing at a point. Okay, and I have a family of them, a vector field, it just varies over, then I can ask what is normal to that family. Then it's a particular hypersurface and not family of them. It's just one. Yeah. Yes.
So like R2 is a hypersurface of R3. What
Yes.
is this called? Like plastic sheet of hypersurface? This is also a hypersurface
Of R3. Of R3. Yes. Of course, I should extend it indefinitely in all directions. But in the spirit of general relativity, we'll be happy with the definition which is in some finite local region. So a small plastic sheet also we can think of as a hypersurface. But if we want to be very picky, that would be a hypersurface with boundary. So I can imagine a hypersurface just going off to infinity. Okay? So this concept of hypersurface, yes.
So hypersurface need not be infinite.
Well, if it doesn't have a boundary, it better be infinite, or it might have to be wrapped in some way. So,
Yes,
for
it
example,
is
a sphere is a hypersurface orthogonal. Yeah, it doesn't have to be infinite. So, a sphere of radius 1 is a hypersurface in R3, whose normal vector is the radial vector. Yeah, so that's also possible. There's a lot to be said about hypersurfaces, and they are very important in physics. So here I'm just reminding you what the concept is, and now, in general, we just say that is the set of all. So the set of all vectors satisfying. Okay, let's start from the beginning. So let's define a hypersurface in the Lorentzian case. Given a vector v mu, the set of all vectors w mu such that w mu v mu equals 0 defines the tangent space to a hypersurface and you can do this point by point. So I have a vector v at many points, in all points. Then I consider the set of all vectors which are orthogonal in the sense w dot v is 0. Okay. Then I ask what is the space of these w's. So there is a bunch of w's. You can think in the simple example, if it was the z pointing vector was v, then the w's will be the unit vector or any vector along the x or y axis. But it could also be any vector in the xy plane actually. So the set of all vectors defines the tangent space to a hypersurface, and I can extend this all over because v is defined all over, and in this way I get the hypersurface. One second. So let's draw a little picture of that. So I take v, and at each point I ask what are all the vectors which are orthogonal to it. Okay. Then these three vectors, let's say we are in 4D, these three vectors will define a 3D vector space. So there's a 3D vector space at every point. Okay, and as a result, when I attach them all to each other, I'll get a 3D manifold which will be my hypersurface. And its tangent space at every point will be those vectors which are orthogonal to my given vector v. So these are the w's. Yes, question.
So a hypersurface is by definition can be embedded inside a larger space. But what if there's a manifold which cannot be embedded in a larger space?
Yeah, the hypersurface is defined by its embedding, so it can't not be embedded.
What if there is a general manifold?
Yeah, let's not go there. I think these are all very hypothetical things. In real examples, there will be such a thing. Yeah.
I suppose v mu in this case will be like a v mu of x.
Yeah, v mu of x, it varies all over in length and if it's not null, it will vary in its length and direction smoothly. It's just smooth. So it's v mu of x. Maybe I didn't belabor this point a lot, but you have already encountered many vector fields. For example, the momentum, we have already studied momentum and velocities of particles. So if I have, let's say I have a, I don't know, I have a situation where it's raining, then the entire volume of 3D space where it's raining consists of has little vectors which are the velocity vector of the falling drops. That is a vector field all over that space. Now I can pick some one parameter family or some subfamily of those vector fields, and I can construct a tangent, the tangent space, or the space which is orthogonal to that vector. And if I pick the family to be one lower dimension than the full manifold, so for example in 3D space I pick a two-dimensional subfamily of these vectors, then I'll define a hypersurface orthogonal to that.
Will this always be true? Like, what if my tangent space turns out to be two less dimensions lower?
You can't, right? If I have a vector, there are always three vectors which are orthogonal to it. If I have a vector in 4D, if I have a vector in 3D, there are always two vectors orthogonal to it, plus a linear some combinations of them also. Remember that at a point, the tangent space is a vector space, so I can add and subtract vectors just at a given point. So when I say the dimension of the hypersurface is 2, that's the same as saying that the total number of linearly independent vectors is 2. Okay, and if the total space is 3-dimensional, that means that the total number of linearly independent vectors is 3 at any point. So if I take one of them out V and I look for all vectors whose dot product with that is 0, the remaining set of vectors will be one less dimensional. That you can't help it. That's just a fact. You can just do it in coordinates. V is some coordinate thing, a comma b comma c. Then the equation w dot v is 0 is an equation, one linear equation in 3 parameters. So it has a 2-parameter family of solutions, and that is these vectors.
Thanks.
So the set of points orthogonal to a vector is always a one lower dimensional surface. Yes. Yes. Yes.
So these three vectors
Yeah.
are the coordinates of the
Not coordinates. They are the tangent vectors.
the three vectors of the tangent.
These vectors are the tangents of the hypersurface. Just think of an example. Think of a sphere. Okay. Think of the radial vector. I ask myself at any point what is the tangent, what is the set of vectors orthogonal to this. Since this points in the radial direction, the two vectors orthogonal to it point in the theta and phi directions. One will point this way along the sphere, one will point that way along the sphere. So it's a two-dimensional space. Now when I fill it all up, I'll get a sphere. Okay? So far so good. That was supposed to be the easy part. Now let's come to the Lorentzian situation for hypersurfaces. This is, by the way, very, very important. You can't, for example, understand the Schwarzschild metric or black holes without this kind of discussion. Now the interesting part is that if V is time-like, now we are in Lorentzian, then the hypersurface sigma orthogonal to it is called a space-like hypersurface. What's the thinking? Well, imagine now I'm in space-time and my vector is along the time axis. Okay, and here I have all of the space x, y, and z. Obviously, anything which is orthogonal to the vector pointing along the time will be pointing along one of the space directions. So this whole x, y, z is a space-like hypersurface in the 4D Minkowski space-time. Is that clear? It's called space-like because everything tangent to it is space-like. And that's a natural thing because I may want to consider some definition of time which is not this one, and then I may ask what is the space-like hypersurface orthogonal to it. For example, I choose my time like that, which will be obtained by a Lorentz transformation. Very simple case. Then of course I'll find a different 3 volume which is orthogonal to it, and that will define the space-like hypersurface orthogonal to the vector along T prime. So it's quite general. I can do this for different definitions of time, and that's the whole point of relativity, that different definitions of time have to be assumed. I mean, they have to be allowed. You can't just fix one time and be done with it. Okay. Now, so if this is time-like, that is space-like. Of course, you can also say the opposite. If V is space-like, then sigma is called a time-like hypersurface. This is little bit more subtle. This is little bit more subtle because if V is space-like, let's say it points along X, then the sigma orthogonal to it will point along T, Y, and Z. So not every vector in that is time-like, but it's called a time-like hypersurface because it has a time-like vector in it. Okay, so these kind of distinctions didn't exist in the Riemannian spatial case, where these words time-like and space-like didn't even exist. Okay, so this is something new. But now comes the real. Okay, so now remember that whatever it is and whatever manifold we have, however complicated with some metric given by some coordinates in some patch, given the vector field, I can construct the hypersurface, and the hypersurface always sits in a space what is called a co-dimension 1 space, 1 dimension lower than the whole space, because the vector is poking out of it. It's like decomposing a manifold locally into some d-1 manifold and a vector poking out of that. So if I translate this everywhere, I'll fill up the whole manifold. That's sort of the geometrical idea. Is it clear? Is it too abstract? This should not be too abstract. Yes?
Is this one vector which you're translating overall, or is it a vector field?
Vector field. I'm given the vector field.
So not every vector field will have a surface which forms, right? You
Why
might
not?
have a vector field where there's like a divergence.
Smooth vector field. Smooth. Divergence is fine as long divergence in, if you mean del dot V is not 0, that's fine. But I can't include the origin from where it diverges because it's not smooth there. That's why we always assume smooth vector fields. So given the vector field, I'm just trying to emphasize that the hypersurface sigma is orthogonal to the vector field. That's what this condition is. The dot product is 0. So it lies in the directions which are, so the tangent vectors to sigma lie along these directions, and V pokes out of sigma. If I want to take sigma and I translate it over V along V, I won't be in sigma anymore. I'll be in some new sigma prime. Okay, it's poking out. That's the important part. Now, what we want to consider is a null hypersurface, and now we get a bit of a shock. Given n mu such that n mu is 0, define sigma as the hypersurface for which all tangent vectors W mu satisfy W mu n mu equals 0. It's the same definition. I haven't changed the definition. It's just that now n is null. Okay? The same definition, you agree? Now, what is surprising about this?
And mu itself will
N mu itself is one of the w's.
Yeah.
Because n mu is given to be 0, but I am looking for the orthogonal hypersurface to have tangent vectors w such that w mu n mu is 0. But one of these w's, again there will be 3 of them, given a null vector n, there will be 3 orthogonal directions, but one of them is n itself. So n mu is tangent to the same hypersurface to which it is normal. It's both tangent and normal at the same time.
Excuse me.
Yes,
I got confused in the 3 part. How do you know there's still?
we are in 4 dimensions. There are always 3 directions orthogonal to one direction because of definition of 4 dimensions.
So what-
4 dimensions means at any point there are 4 linearly independent vectors.
So what are we fixing? Then because we are in TXX.
Let's say we could be in Minkowski spacetime or we could be in any Lorentzian spacetime. So it's 4 dimensional. Sorry, I keep going between 3 and 4 dimensional examples. I don't know.
I got confused because I don't know now if a space dimension I am fixing or if a time dimension is what I am fixing.
I'm not fixing anything. I've chosen a null vector field. So I have it everywhere. And I look for the tangent vectors, which the hypersurface, such that its tangent vectors w satisfy w dot n equals 0. Simply that. Now the problem is that w dot n equals 0 is an orthogonality condition, right? We call it w dot n. This is w mu n mu. We call it w dot n. But actually n dot n is 0 because it's a null vector. So n is one of the w's. So out of 3 w's, one of them will be n itself. Okay. Now this looks terribly abstract, so let's make it concrete. Let's go to 4D Minkowski spacetime and let's take n mu equals 1, 0, 0, 1. Can you give me a list of the 3 vectors which are orthogonal to this? Please.
0, 1, 1, 0.
Good. So you want 0, 1, 1, 0, okay?
Okay, yeah, it's better if we do
0,
0, 1, 0.
Thank you, much better, yes.
0,
So
0,
W
0.
mu,
Yeah.
this is 1, which is points along the x-axis, so it doesn't know anything about t and z. And it's certainly orthogonal to that, because this doesn't hit that. Then there's another one which is 0, 0, 1, 0, which is along the y-axis.
Yeah.
Both are in the hypersurface. And the third one,
Minus 1.
And mu itself.
Minus 1, 0, 0.
is that orthogonal to 1, 0, 0, 1?
We make
No,
it-
1 minute, what he's saying. You're saying minus 1, 0, 0, 1. Is it orthogonal to 1, 0, 0, 1?
Okay.
Okay. It is 1, 0, 0, 1 itself. This is orthogonal to this. And once you have this list, you are done. There can't be a 4th vector which is orthogonal in 4 dimensions. There simply, you cannot have 4 solutions to the equation w dot n equals 0. There can only be 3 solutions. Okay? And those 3 solutions can be chosen to be these. They're not unique by any means. Any linear combination of these will also satisfy. It's a linear condition. So it's a tangent space, so any linear combination is also in the same tangent space. But the point is that certainly the original null vector is also in it. So we have the weird situation that if this is a null vector n, then its hypersurface orthogonal to it has n as one of the directions, and then there will be 2 others. And those will typically be space-like, as you see here. These 2 are space-like vectors. This is null. And so the null vector, so a null vector, I said it here, is tangent to the same hypersurface to which it is normal. But now we seem to have only accounted for 3 things in W. So the null vector is no longer poking out. It's not poking out, it's poking in. It's just sitting in its own hypersurface. But something must be poking out because there have to be 4 linearly independent vectors. So you mentioned a vector just now, n prime mu, we'll call it, which is 1, 0, 0, minus 1. First thing to note is n prime is also null. And second thing to note is that n prime dot n is non-zero. What is it actually?
Like 2.
What is n prime dot n?
Minus
Minus 2. You shouldn't be slow on this, so close to the exam. N prime dot n is just minus 2. This is Minkowski example. This is an example. You must also learn to distinguish my examples from the general theory. Okay? But it will, what I will claim without proof is that these examples, the properties remain true in the general case. Okay. So here is n prime, and supposing I was to draw it. So now let's try drawing these honestly in the Minkowski case. And so it's, I'm sorry, but this is how we have to draw it. So now the ZT plane is gosh, it's very difficult for even me to visualize.
N mu is like between Z and T, and n prime mu is like the other way.
Yeah. So exactly. So imagine the TZ plane, then n is like this, and n prime is like that. Okay. And of course, these two vectors 0, 1, 0, 0 and 0, 0, 1, 0 are like this. Okay. So the span of this and that is the null hypersurface, and this is poking out of it. So I can think of the null hypersurface as this sort of translated along y and x, and this is poking out of it, but it's not orthogonal to it. So n is tangent to the same hypersurface to which it is normal, and n prime points away from sigma, but is not normal to it, not orthogonal to it. You would think that pointing away, a vector pointing away from a surface could always be chosen so that it's orthogonal because this angle is 90 degrees. Problem is, these are not angles in Minkowski spacetime. These are angles that we are imagining because we are seeing this system in Euclid. In our mind is a Euclidean metric. When we see two lines like that, we say 90 degrees between them. That's not how it actually works in Lorentzian spacetime. As long as time is involved. If you are working only in x, y, z, everything would be normal. As soon as time is involved, these crazy things happen. So, summary, the vector which is tangent to a hypersurface is a vector which is normal to a hypersurface is also tangent to it. The vector which points out of a hypersurface defined by n, there is a vector which points out, but it's not orthogonal to the original one, but it does point out. And that has a meaning because I could ask, what if I take this null hypersurface defined by n and translate it along n prime? That I can do. And I'll go to a family of hypersurfaces which will be all different. So there's a meaning of pointing out that given this hypersurface, if I go along n prime, I don't remain in the same hypersurface as I was before. So that's what pointing out means. Okay, but unfortunately it's not orthogonal to the original, so we have to just keep that in mind. So n prime dot n is -2 in this example. More generally, the general statement is that when you have a null vector and it defines a hypersurface, it's tangent to it, and there is another vector n prime, which may or may not be easy to construct, which points out of that hypersurface. So this is the situation.
Is the other vector always going to be like
Null. I can choose. See, there are many choices available to me. Thank you. So you said always. So let's understand a few things. First of all, let me say that this is a null. A hypersurface which is orthogonal to a null vector is called a null hypersurface. Does it mean that every vector in the null hypersurface is null? No. It means exactly one linearly independent vector can be taken to be null. I can also take all of them in different directions such that nobody looks null, but the null vector n itself will be there in the linear span of these three. I invite you to choose other bases. Actually, I can do it for you. Instead of this n, I could have just chosen this one. Okay, sorry, this is no, sorry. I have to choose a vector which is orthogonal to this. Sorry. So actually I have to choose, no, n prime is not in the surface. I'm saying instead of these three, I could have chosen these three.
You can add the first two.
I could have chosen this. Good. I could have chosen this as my third one. Exactly. This is not null, but it's still orthogonal to this because 1, 1 and 1, 1 will give me 0 by the Minkowski metric, and this dot with this doesn't give me anything. So this is an example of basis of three vectors in the null hypersurface, none of which is actually null.
I asked for n prime actually. So
Yeah.
will n prime always be?
So what is n prime defined as? I've defined it as the null vector poking out of the hypersurface. If you just want a vector poking out of the hypersurface, it's much easier. You can choose 1, 0, 0, 0. That also pokes out of the hypersurface. Anything which is not in the linear span of these three vectors will poke out of the hypersurface. But the important result is that there is a null vector which points out of the hypersurface.
Why do you want something null to point out?
It turns out to be useful. I told you, null vectors all will be associated in relativity, general relativity, with light propagation. So we will find that if we consider the tangent vector to a light ray, the null hypersurface orthogonal to that contains the light ray, but there's another light ray which points out. It's nice to know that. In fact, it's crucial to know that. This is a root of Penrose's famous singularity, black hole singularity theorem. The fact that there are two light rays, one of which lives in a surface, but the other points out. Yes.
Is this thing like easier to see in that light cone coordinates which we do?
Yeah, it is actually. It is very much so. Very much so.
Those two rays.
Absolutely.
That
Is absolutely easier to see. And in fact, that's what I was going to do next. So what you have just asked raises a question, which is what I wanted to do next anyway, which is, these are vectors in some given coordinate system. Can I make a coordinate system in which the coordinates themselves are null? It's the same as your question if you think about it. Because in that case, translating a coordinate will correspond to going along a null direction. And this statement should tells me that I can locally at a point, at least in simple examples, I can find two null vectors, null coordinates. And actually we'll see that is true. But it may not extend in complicated spacetimes, that may not be so easy. Let me show you some examples first. So good. So coordinate systems. So let's state the question as follows. Can we choose or can we have a null coordinate? We are used to the fact that when we look at Minkowski, for example, or when we look at anything we have been dealing with, there's one time and three space dimensions. We always write the metric in terms of Ct, x1, x2, x3, and then t ends up always being the time direction, and the others are space. So none of them is null. None of the coordinates is null. So let's ask it the other way. Supposing somebody gave you this metric. They said, I have two coordinates u and v, and this is my metric. What can you conclude from this? Two-dimensional space, obviously. Space or space-time, that's up to us to find out. I've given you some exercises in the exams and quizzes to find out the signature of a space-time. And this is an example. I don't know, did I give even this example? No. Okay, now I'm giving it. What is the signature of this? What is the space-time? How do I think of it? Huh?
Is it 0, 0?
It's not. If it was 0, 0, then the metric would have to be 0. Any metric whose eigenvalues are 0 and 0 is 0, and this metric is not 0.
It is +1.
Signature is +1. What do you mean?
I said determinant is
Determinant is +1. Really? How do you get that?
So off diagonal terms will be minus half.
Yes.
Not +1, but like
Not like what? It's important.
a quarter.
No. But plus or minus?
0 minus six.
Good.
minus
I'll follow your instructions. 0 minus half minus half 0. This is the metric we agree for this. This is G mu. What is its determinant?
plus a quarter, right?
You keep saying plus a quarter, but it's minus a quarter. There are lots of minus signs in life.
Sorry.
Yeah, very good. But good you brought it up. That G is minus 1. That's an elementary exercise. So what is it?
Minkowski-like.
Minkowski-like. Superb.
Actually, we can do u plus v and
Exactly. Exactly. So let u be ct minus x and v be ct plus x. Then I get the same metric becomes minus c squared dt squared plus dx squared. Where have we seen that metric before? So what have we actually done? We have taken Minkowski spacetime with this being x and this being ct, and we have taken these two directions. Okay, so which one is which? Well, the line, so if u is 0, then ct is equal to x. So that's this line. So this has u equals 0. So this is the v-axis. V can vary, but u is stuck at 0. Sorry for my bad drawing. V-axis, u equals 0. Just like x-axis is t equals 0, t-axis is x equals 0, v-axis is u equals 0, and here we have v equals 0. So this is the u-axis. So I actually changed my coordinates to these two axes. Okay, and what are these axes in 2 dimensions? What you said, the light cone. It's not a cone because I'm in 2 dimensions, but I can easily repeat this in higher dimensions using the radial vector along with time to define u and v, and then I'll get the light cone. Okay, and so what I've done is that motion along this is a null direction. First of all, this is the direction along which u is 0, so ct is equal to x. So only light can travel. Ct equals x is the same as dx by dt is c. So only light can travel. And here also. Now also we can look at this diagram and get some physical picture. We are in 1 plus 1 dimensions. So there's only one space dimension and there's time. Okay. So what is light traveling along the v-axis? What is it actually doing physically? Where is it actually going? It's going along positive x. That's exactly right. In the future. In the past, it goes along negative x. So it came from negative x and went along positive x. This slope tells me that x is increasing. So it is a light beam that starting from some place goes towards the positive x side and goes on till infinity. This is also a light beam, but it's going along negative x into the future. Okay. Now we know that light beam in 1 plus 1 dimension should be able to go along positive or negative x. There are no third choices. There are no direction it can go in. The only space direction is x. Okay. So there are 2 linearly independent choices for light, and one is this and one is this. This also gives you an insight into why there can be 2 different independent null directions. Okay. But the problem is that this axis along v is its normal vector is the vector along it. It's not a problem, it's just a fact. It's what I proved earlier. In this example, a hypersurface is a line, and the line orthogonal to the vector along v is the same line. And this is the one poking out. Now you asked earlier that can there be other vectors poking out of this line? Of course there can be vectors like this or this or this. Lots of vectors that poke out of it. Okay, even this pokes out of it along x. So many things are possible, but only one of them is the null direction. So this illustrates what we are doing. Now there's a lot more that I have discussed in the notes in the context of, there's one last thing I need to discuss and then we'll come to, then I'll just leave you to read the notes. So these I'm doing simple examples in 2D. Okay, so here we had this definition, and this took us between this metric and the metric minus du dv. Now there's a name for this type of coordinate system with u and v. It's called double null. Because there are 2 null coordinates, If I extend this to 3 plus 1d space, say space time, there'll be a u and a v, and there may also be a theta and a phi. Okay, if I choose this definition with respect to the radial coordinate r, then there'll be left over a theta and a phi. Those are definitely not null, they are space-like coordinates. Right? So it's double null. There's also something called single null, which is very surprising when you see it first time. And it's useful, may not be useful in this course, but it's useful in general. So let's do this. And now let's set u equals ct minus x and x equals x. In other words, from the coordinates x and t, I go to the coordinates x and u without changing x. I only replace this combination by u. So my final coordinates will be u and x. Now let's see what we expect from the metric. So to find that, we just write ct is u plus x. So here I get minus du plus dx squared plus dx. Let's work it out. This gives me minus cross term 2 du dx minus du squared minus dx squared plus dx squared. These cancel and I get minus 2 du dx minus du squared. Now, what is null in this new coordinate system?
U.
Really? It's a surprising statement. Du squared is there in the metric, so if I move a distance along u alone, I'll change ds squared. How can you say this is null? How do I recognize which coordinate is null given a metric? D of that coordinate squared should be absent. If it's present, the coordinate is not null. Right? Is that clear? What means time? The coordinates are u and x. You have to tell me what is null between u and x, if any. X is null. X has become null. In the new coordinate system u and x, since these are such simple examples, you should sit and draw the axes on your own and you will see why it happens. Okay? Remember, the important point is that when we say x is null, it means moving in x, keeping u fixed. Right? Here, we were moving in x, keeping t fixed. These are not the same thing. When we ask if a coordinate is null or not, we are asking if I move along that coordinate, keeping all other coordinates fixed. But what I keep fixed has changed between this and this. Here it was t if I vary x and x if I vary t. Here it is u if I vary x, I keep u fixed. But if I keep u fixed, then from this I see that I'm not keeping t fixed. On the contrary, t has to remain equal to x. Okay, if ct is always equal to x plus some constant, I'm always moving along a light cone. So that's ultimately the reason why x has become null. Okay, and this is a toy version of what are called Eddington-Finkelstein coordinates. Of course, it's a completely trivial statement for, we are doing just Minkowski space-time. But these coordinates are useful in Schwarzschild space-time, where we actually have a transformation to such coordinates. And this kind of thing, as you can see, should be called single null, because only one coordinate is null and other one is not null. So this is single null. And in fact, this is called outgoing Eddington-Finkelstein, and it's an exercise for you, though I've just told you the answer, to find out why it's called outgoing. Can you also guess what is the ingoing one?
Ct plus x times.
V is equal. So always this is a convention just to match with all the literature. U is always t minus x and V is always t plus x. So if instead of this I did V equals Ct plus x, then I would simply end up with 2 dV dx minus dV squared. And these I claim are called ingoing Eddington-Finkelstein coordinates. But I do want to emphasize that these aren't, I mean, people will laugh if you go around telling them that in 2D Minkowski we have some ingoing and outgoing coordinates, because what are they outgoing from or ingoing to? There isn't anything there, it's just empty space-time. They are ingoing and outgoing with respect to some chosen origin, that's all. Okay, but if you do this when there is a Schwarzschild solution, then you have a gravitating body, and what you do is the solution, okay, Schwarzschild is more complicated, but this is a standard thing, right? We can write Minkowski like this. Now in this metric, we'll define, for example, U to be Ct minus R, and R equals R. Then I'll get dV dr minus dr squared plus R squared, all that stuff. This is the true Eddington-Finkelstein metric. du, sorry, this is minus E. This is the actual outgoing Eddington-Finkelstein. And sorry, wrong number. This is E. And so what we find is that the radial direction in this metric is null. It's called the null radial direction. And as I already told you, it's not that mysterious. It just means that when I travel along R keeping U fixed, then my time is also increasing along with R to keep pace. And therefore, I'm actually traveling into the future as well as radially outward. I've answered the question why it's called outgoing. Outgoing or ingoing are defined with respect to the future. If you're outgoing in the future, obviously if you go back to the past, you'll be ingoing and vice versa. But we are asking, where is this light ray heading? So the light ray, as I vary R, is null, as it should be, and T increases. That means that I'm moving actually into the future with R increasing. On the other hand, if there was a plus here, I would be moving into the future with R decreasing. That would be ingoing. Yeah.
So in the previous metric, there was another line also along which the ds square is 0.
Yeah, that line is there, but it's not a coordinate in this coordinate system. In the du dv coordinate system, there is such a thing, right?
Yeah.
So here we are choosing coordinates. It's up to us how to choose coordinates. First thing is that in this one, there is no null coordinate at all, right? That doesn't mean there are no null vectors, right? They are there. It's just that none of them is a coordinate. What you have to understand is that a coordinate means I'm moving in a particular direction, keeping all others fixed. So here, if I move in any of t, r, theta, phi, keeping all the other three fixed, I never move along a null direction. But doesn't mean the null directions are not there. They are of course there in this metric. But for that, I have to move along at least two coordinates together, like r and t. However, once we get a null coordinate, it is a coordinate, in this case r, along which if I move keeping the others fixed, this ds squared doesn't change at all. ds squared doesn't depend on dr squared. So any motion along dr will not give me any interval ds squared, and therefore r is a radial null coordinate. And as I said, physically it is the coordinate along which light will actually travel, because of this fact that when r is changing and u is fixed, t is also increasing with r. Let's say that u is fixed to 0, then ct is equal to r. So when I change r, automatically by keeping u fixed, I'm also changing t, and so it's going into the future. As I increase r, it is also increasing, so I'm going into the future. And I'm increasing r, so it is going out as well. So it's a very subtle thing, yes.
Can we also define such null coordinates with respect to theta and phi?
That's much more, thank you. So can we combine t with theta or phi? Unfortunately, that will mess up a lot of things because these are periodic, these are angle valued. So we'll have to impose some very weird conditions on this u. You can try it, but you'll have to impose some weird conditions that u comes back to itself after 2 pi because of shift in theta. So u and u plus 2 pi you might have to identify. But it's more complicated than that, because then u plus another coordinate, say v, if I add them and cancel out the theta dependence, then it's no longer periodic. So when you have coordinates which depend on an angle and also on another thing which is not an angle, the condition on that coordinate is very complicated. It's not very convenient usually. But yeah, it might be convenient for some given problem. Okay, as usual we went slower than planned. So I need to say a couple of things, otherwise we won't have any time to do what we are doing next time. So give me 2-3 minutes.
R is
Yes. So actually there's just one key observation, two key observations. Let me just say that. Supposing this is a light ray. Along this light ray, at every point on its trajectory, I am at some space-time point x mu. How do I parameterize this? What do I use to label points along the light ray? We've done it before for geodesics, which were time-like, and we use the proper time. Now we can't, even if this is, I didn't say it's a geodesic, but it could be a geodesic. But I can't use the proper time because whether this is geodesic or not, if it's a light ray, its proper time is always 0 because it's null. So I can't label this trajectory by the proper time. So what should I label it by? It's a very big question.
The double null coordinates, the coordinate in the double null.
I don't have to, I don't want to do it in any fixed coordinate system. X mu is an arbitrary coordinate system because remember, I'm not trying to make my equations in a fixed coordinate system. I want my equations to be general relativistic. They should be completely independent of choice of coordinates.
Not the coordinate.
Also, I'm only trying to label points on this. I'm not trying to label every point in space-time.
No, but you could use the corresponding point for that.
I could, if I had double null coordinates.
If not the coordinates, then by the vector which is in the opposite direction, which points out of the hypersurface.
Same thing, that's not unique. Yeah.
The hypersurface, and then we could. So we have 3 directions in the hypersurface.
Yeah.
We can use the 2 space-like
Yeah.
directions and parameterize that, and that would tell me.
You could, but under change of coordinates, it would change to something else, right? With the parameter which labels remember tau, what was the usefulness of tau in the time-like geodesic case? It doesn't change under any change of coordinates because d tau is g mu nu dx mu dx nu, d tau squared is that. So it's invariant, it doesn't depend on coordinates. So I need something that doesn't depend on coordinates.
The hypersurface. Isn't it like
What hypersurface? The light is traveling along the hypersurface to which it's null. It's much simpler than any of you think. I just pick an arbitrary parameter and call it lambda and just let it vary and increase smoothly along the surface. Over. The only problem I have to worry about is whether this parameter is going to, whether the physics answers are going to depend on the parameter. That we'll worry about later. Okay? So we just pick an arbitrary parameter. Real parameter. It doesn't depend on any coordinates. And it should be increasing smoothly along the trajectory. Okay? So now x mu is x mu of lambda. Now I want to define the velocity of this light ray, and using what we did earlier, we'll just say that u mu is dx mu by d lambda. So far so good. Now we come to an interesting issue. Now what is u mu? U mu. I told you that in the time-like case, u mu can always be, is always equal to minus c squared. It's a constraint. But that came only because this was tau and not lambda. It was the proper time. Now on the other hand, this is g mu nu dx mu by d lambda dx nu by d lambda, and this stuff in the numerator is 0 because it's null, and so u mu is 0. And this is good. The four velocity of light is a null vector. A very natural definition. Okay. The only thing is we have to accept the fact that u mu was always minus c squared for any massive particle, and it suddenly has jumped to 0 for a photon. and it didn't actually suddenly jump, because earlier it was dx mu by d tau, but I was allowed to scale tau. I think it was an exercise to show that if I scale tau by any multiplicative factor, it will still be an affine parameter and same geodesic equation is satisfied. Okay, so therefore I could actually have made u mu to be minus anything other than c squared, even minus 0.0001. I could make it very small, but I can't make it exactly 0. There's no meaning in taking tau and scaling it by an infinite amount. You can't scale a number by an infinite amount, it won't remain a number. You can scale it by any finite amount. So I could make u mu equal to anything negative for a massive particle depending on my choice of parameter. But for light, it's stuck at 0 and I can't make it anything else by scaling lambda. It won't change from 0. It's always 0. U mu is always 0. Okay? And now comes sort of a punchline. What is p mu, the momentum? Surely we all believe that light has a four momentum.
Yeah.
But it used to be m dx mu by d tau, but m is 0. M is the mass of the particle, and here it's the photon, and the photon has mass 0. So are we going to say p mu is 0? This is very worrying because, and by the way, these are all things you can even discuss in special relativity, not just general relativity. It's very worrying because p mu should have energy as its 0 component in some frame. So it can't be 0. So we do a very weird thing. We say that p mu is just equal to u mu. The momentum is the same as its velocity. Actually, we do something different. We say it's any quantity a times u mu. Therefore, it is a times dx mu by d lambda. And now it follows that the four momentum of light is null, just like u. And that's good. Because if you remember, what was the square of four momentum of a particle of mass m?
Minus m squared c squared.
Minus m squared c squared. So when m is 0, it just has to be 0, and this it follows. A is a bit puzzling. So whatever A is, this is always true. This is again an example of you can't normalize a null vector. Whatever you do to the null vector by multiplying by a constant, it will just remain null. Nothing will change about it. So to simplify our lives now, we just declare that A is 1. Now this raises a new problem, and with that I'll stop. With this has dimensions of 4 velocity and this has dimensions of 4 momentum. How can that be? Because finally we are going to take this and we are going to use it for some measurement. Otherwise it's a completely useless idea. So there is a way out, and next time you will see why we choose that way. So what we do is that we actually say p mu is dx mu by d lambda, and lambda has dimensions of time over mass. If you give it these dimensions, then it's fine, because now time is here, mass is there, so it's mass times velocity. That's the correct dimension of momentum.
Then velocity has
Yeah.
to-
So velocity is dx mu by d lambda, where lambda has dimensions of time.
Okay, then
It doesn't, nothing depends, since I'm going to show you that nothing depends on lambda, can have any dimension it likes, as long as, I have to still show you, it's nothing obvious. In fact, probably we'll only see it on Saturday in that lecture, why nothing depends on lambda, because we have to see what we can observe. What do we observe of light? We have to be in a rest frame, we have to be in our frame, and light has to come, and in our coordinate system, we have to observe it and measure its energy. And that should be possible, that will be possible independent of what lambda is chosen to be. By the way, you could find a contradiction if you could go into the rest frame of light, but guess what? You cannot.